Okay, so let me start today. So before we begin, let me clarify one question that was asked the last class by one of the students. So the premise is this. So let's say you have the 5 transistor diff amp. And for this diff amp, when we are trying to look at the pole zero locations, so we basically considered a differential input, right? And we told that if we ignore the R0 for the NMOS transistors, what can you say about this node? That is at 0. So we told we can simplify the circuit to be this, right? Virtual ground. So let me, okay, fine. Let me copy paste this. Yeah. So now we consider only 2 capacitors, one at the output and one at this side. So we told that the dominant pole here was the total output conductance by CL, and the non-dominant pole here, what was the location? It was GM of that PMOS by C, because looking in it's just GM of the PMOS, right? Oops, sorry. This was GM of the PMOS by C3. Okay, but we are also seen in one of the classes that, let me actually draw the circuit again. So in one of the classes we also looked at the total impedance looking here, right? And for finding the impedance I will not consider the inputs. And what was the total impedance? It was 2 GM. That was basically because if I apply a test voltage here, this transistor will take in a current GMP times the test voltage, and I'll ignore R0, so this no other current flows here. But this voltage is also applied to the gate of the other PMOS, so that will also generate a current GMP V test. And I mean, if you ignore all the R0s, this current will have to come out this way. So the total current that this test voltage has to supply is 2 GMP times V test, right? So the impedance we found was 1 by 2 times GM of the PMOS, right? Well, so now it makes sense that, I mean, for pole calculations, I mentioned there is no point of, I mean, it doesn't matter what the input is. And the way we have been finding the pole is we look at the impedance at the node, the conductance at the node, capacitance at that node, take the ratio. So here it looks like the conductance is 2 GMP, capacitance I considered as C3. So shouldn't the pole be at 2 GMP by C3? Makes sense, right? So what's the catch? I'll tell you for a fact that both these statements are correct. Okay, if I find the impedance looking here, it's 1 by 2 GMP, and the non-dominant pole is indeed GMP by C3. So what's the catch? What do you think? Okay, so let me probably see. Here we are now trying to look at the non-dominant pole, right? And that means that by the time I encounter the non-dominant pole, the capacitor which contributes to the dominant pole, what can you say about it? It acts like a short, because we are looking at a frequency high enough that the dominant pole has already contributed, has already come. So this capacitor acts like a short basically. Okay. So now if you try to apply that same test voltage, it is true that this transistor will generate a current GMPVT, but where will this current now flow? It will basically flow to the short. Okay. So none of the current will actually reach the other side. This will be 0. That is, the contribution of GMP here will be 0. So around that frequency, the conductance will be only GMP. Okay. So that is why the non-dominant pole was actually at GMP by C3. That's fine. And this was basically very similar to the cascode case, right? So even in the cascode, we had a dominant pole at the output, a non-dominant pole here, and we saw that the conductance looking into this node was basically equal to 1 by GM, and was conductance was GM, because although the actual impedance looking into the source depends on the drain impedance, right? Since we are looking at the non-dominant pole, this capacitor basically acts like a short. So the drain is shorted, the impedance is 1 by GM of this transistor. The same thing is happening here. Okay. Cool. So with that, let's continue from where we left off. So in the last class, we looked at the schematic level implementation of the two-stage Miller op-amp. So we had started with an NMOS differential pair for the first stage. So let me draw that. So if I use NMOS for the first stage, what was the second stage? It was a PMOS common source, right? Because we saw that the first stage, the DC level at the output of the first stage lends itself to a natural voltage level that is compatible with the PMOS second stage. And if you had started with an PMOS first stage, the second stage will be NMOS, right? And the compensation capacitor was added here like this. So let me quickly label the transistors: M0 to M1, M2, M3, M4. This is M5 and M6. So how is this DC bias set finally? That will be set by the DC negative feedback we'll have around the op-amp finally. And if we here we have two inputs, A and B. So what is the negative terminal? A, right? Because if you increase the potential at A, from gate to drain there is an inversion, so the drain voltage drops, so which means this gate voltage is also dropping. That will mean the corresponding drain will increase, so this increases the gate of M5. So the drain of M5, which is the output, drops. So A is the negative terminal. So to form the negative feedback, I'll basically go ahead and make the connection like this. Okay. And at the other terminal, I'll apply the common mode, which we saw will be roughly at VDD by 2. So this guy will be set to VDD by 2 ideally. And we saw this will be equal to VDD by 2 if we make sure these two potentials are equal, right? We saw that if these two guys are equal, there will be no offset between these two, else there could be a systematic offset. And what was the condition to make sure that these two voltages are equal? How will I design the current densities for the PMOS transistors? Basically all these PMOS transistors must have the same, so let me write M3, M4 and M5 must have the same I by W by L. So if the L is same, I need to make sure the current densities are equal. Right. So here let me probably shift here. Yeah. So now if I were to draw an equivalence to the block level two-stage OTA that we have been looking at, let me quickly draw that block level implementation. This was the deal. So this was GM1, GM2, this G1, C1, CC. So we have G2 and C2. So what is GM1 in our transistor implementation? Small, I mean GM of the NMOS of, GM of the transistors M1 or M2. That's the first stage. What about capital GM2? GM of the transistor M5. What about the conductance G1? Let me erase these guys, simply cluttering. Yeah, G1 is the conductance at this node. What is the total conductance at that node? R04 parallel R02. So in terms of conductance, I'll write it as GDS4 plus GDS2. That's all. Okay. What about G2? So that's basically the conductance here. R05 parallel with R06. So that is GDS5 plus GDS6. What about C1? C1 is the capacitance at this node. What all parasitic capacitors will be present at this node? Which all transistors will contribute? 4, 5, 4, 2 and 5, right? So from here you will have a drain to bulk capacitance of 4, drain to bulk of M2, and also we have a gate connection, so the gate to source capacitor of M5, right? So you'll have drain to bulk of 4 plus drain to bulk of 2 plus CGS of 5. So which of these do you think will dominate? Gate capacitance will dominate. Okay, that's the largest. So this almost entirely will be dominated by CGS5. Cool. And what about C2? That will, okay, good question. He's asking about CGD, but CGD will come in parallel with CC, right? Okay. So what about C2? C2 is a total capacitance from the output to ground. No CC. I mean CC is additional capacitance that we are adding, right? I am just looking at the total capacitance from this node to ground. Yeah, okay. C2 is basically the drain to bulk of M5 and drain to bulk of M6. Okay, CDB5 plus CDB6. So now in addition, you can also have the load capacitance and load resistor, so you can connect it. So load resistor, let's say we have RL. From the output we'll connect it. And what about the other terminal? Where will you connect this to? Okay, so if you connect it to ground, at DC, this is at VDD by 2. So this will start drawing a current and it will disturb all your biases. So where do you think I should connect this to? I don't want to draw any DC current. Where should I connect it? I mean, the question is simple, right? So this potential is at VDD by 2. Is that okay? I am saying that at DC I don't want any current to flow here. So where will I connect it? To what potential I will connect it? VDD by 2. I mean, you can also do this AC coupling and stuff, but that will require huge capacitors. On ICs we can't afford to spend so much area. Okay. So that's why we will simply go and connect it to VCM. Whatever that common mode is for us. In our case it's VDD by 2. Okay.
So if there is an offset, like vanishing the offset currents there.
That will be still very small. You need to ensure that it's small enough. That's all. And you'll also have a load cap, so you can do that. Okay. And remember, when you try to look at the stability, you should also consider all these load impedances, right? Because for stability, basically you'll be looking at the loop gain that you will obtain by breaking the loop, injecting a test voltage somewhere here and finding what comes out. So in the two-stage equivalent, along with the intrinsic G2 and C2, should also include the load conductance, load capacitance. So all your phase margin and all calculations you should do including all these, right? Great. So now we have we have arrived at a two-stage op amp which can be made stable. We know how to do it, and we kind of did that by putting this capacitor CC that made sure that the two poles in open loop, they are far apart. But in that process, have we introduced something else to the system? Huh? So we have put this capacitor CC to split the poles, but in that process, have we introduced something else to the system? No, not. We have also introduced the right of plane 0, right? And where is the right of plane 0 at? I mean, in terms of this block. Oops. There is a 0. First of all, logically, why is the 0 coming? Sorry? We have two paths for the current. One path is from GM2, one path is from CC. So logically, the 0 must be dependent on those two guys. So what is the 0 frequency?
GM2 by CC.
That's all. Okay. And this right of plane 0, as we saw, is a bad thing because that will add phase lag and delay and will degrade your phase margin. So people have had so many years to think, and they have come up with techniques to eliminate this right of plane 0. So let's look at them. And for that, I'll only consider the second stage because that's what contributes to the 0, right? So first let me draw that. So this is my GM2, this is CC. So as I mentioned, we have this 0 here because we have two paths for the current, one through GM2, one through CC. And at the 0 frequency, this guy is 0. So what is the current coming out of GM2? If this voltage is some V1 minus GM2 V1, what is the current coming from the capacitor side? D1 times SCC, and both of them will add to give 0, and that's why the 0 frequency was GM2 by CC. And this 0 is basically at the right of plane because the current from one of the paths has a 180 degree phase shift compared to the other path, right? The capacitor is providing basically 0 degree phase. The GM is providing a current that is 180 degree out of phase. So the bottom line is we have the 0 here because we have a path for the current to flow in this direction, right? And if you remember, the reason we put CC was we wanted this Miller effect, and for Miller effect we need to put something in feedback, right? So we only want basically the current to flow from let me erase it. So we actually want the current only in this direction. We want only feedback, right? But we also have a current in this direction, and that's simply because we have a capacitor. Capacitor is a bilateral element. It doesn't differentiate which direction signal flows. It will allow from both directions. And the same is true even if you use a resistor. So if you have a resistor also like this, so even in this you will have currents flowing in both paths, right? So here if I call this some V1 again, can you do you think this V out will be 0 for some condition? No, I mean that is one trivial case. Okay, so if this is V1 and V out is 0, again what is the current coming out of the GM? GM2 V1. What is the, if this is some R, what is the current coming out of R? V1 by R. So if this is 0, what is the condition? R is 1 by GM2. I mean, one trivial case is when V1 is 0, but we can also have the output go to 0 if R is 1 by GM2. I mean, the same thing. And in fact, this was your first mini quiz question, right? I had given something like this, isn't it? I mean, this is basically same, right? This is your GM2, this fellow, and around it I put a resistor in feedback, which is this, right? And this is true even if you form an inverting amp using VCCS, that is using our OTA. If you form an inverting amplifier like this, so ideally you expect that we will have only feedback. Let me push it down. So ideally you expect you will have only feedback like this, but because of this resistor we will also have a feed forward. Okay, so the classical feedback model, which models a feedback system like this. This is A, beta. This is actually no longer valid because you not only have a feedback, you also have a feed forward. Okay, so to model that feed forward path, you actually have to add some other thing like this. Because the resistor is not only contributing to beta, but it also contributes to some signal transfer in the forward direction. Okay. But if you actually notice, if you were to use VCVS, so if you were to form the same inverting amp using VCVS, so let's say this is ground. Something here. So even here the resistor is going to conduct in both directions, right? But if you use a voltage controlled voltage source, if this is at some Vx, what can you say about this voltage if the gain is A? Minus A times Vx. So the output voltage will be fixed to this minus A Vx irrespective of the current that the resistor conducts in this direction. Okay, this voltage is fixed, so it doesn't matter what current the resistor is conducting in the direction, and being an ideal voltage source, this can sink or provide any amount of current, so no problem. Okay, but when you have a VCCS like this, that is only providing a constant current. Okay, so if along with this current, if you have some other current flowing from the resistor, both the currents will add up, flow into the effective resistance at the output and generate the output. Okay, so that is why you also, I mean, this feed forward is a problem here. If you have a VCVS, the forward transfer due to the elements you put in feedback, that's not a problem at all, because the forward voltage is kind of fixed constant by the voltage control voltage source. Is that point clear? So the bottom line is, if you use a VCVS, it ensures only feedback. And no feed forward. So now we know a couple of things. One, in our two-stage OTA, we have this voltage controlled current source. So this capacitor is adding current in the forward direction, and that results in a 0. We also know for a fact that if we were to have a VCVS, there is not going to be any feed forward. So can you think of a way to avoid this 0 now? But I mean, we already have a VCCS, so what do you suggest we do? His point is correct. He says if you use a VCVS, there is no feed forward, there will not be 0. But we have already started with the VCCS, right? So what is the simplest thing you can do? Okay, but that will not. You need to put a buffer. Okay. See what he's saying is this is our GM. If we were to make this connection directly, we are gone, right? And when we had a VCVS, we didn't have an issue because the output voltage here was fixed by something. If we have some kind of a voltage source fixing that node, we have no issues. And the simplest way we can have that kind of a voltage control voltage source is to put a buffer, right? Because we know how to form a voltage buffer using transistors. We'll put a buffer and make the feedback like this. Now this buffer will fix this voltage to something, so we'll not have a feed forward. I mean, other way to think is this buffer is only going to allow signal flow in this direction, right? It will not allow signal in this direction.
The current coming from that VCVS cannot flow the buffer.
No, buffer. See, buffer is a voltage source, voltage controlled voltage source, right? An ideal voltage source can provide or sink any amount of current. It's a voltage source, right? This is the connection we are making.
It will not be able to take the current from the VCVS, right?
That is okay. We don't want. I mean, here we have a resistance. The voltage is what is getting buffered. We are finally interested in the voltage. Yeah. That's I just inherently assume that. Okay. So bottom line is this voltage buffer will only allow signal in this direction from input to the output. It will not allow the thing in the other direction. Okay. So, but yeah, this is a nice way. But again, as I mentioned, in practice, this buffer cannot provide a gain of 1. Say it gives gain of 0.7 or something. So let's say you design this to have a gain of 100. So at this point, you might have a gain of 100. But at this point, you kind of lose something. So what do you suggest we do? Sorry, quite common source to increase gain. That will again add more stages and it will introduce poles, right? I mean, what is the simplest thing you can do? I mean, if I take the output from here, I see that the gain is reduced. I'll say that my output is not this. If I undo one more time, I'll get it. Yeah, I'll call this as my output. That's all. Okay. So as you'll see, there is one other reason why you might call this as the output that will be apparent if you look at the schematic implementation. So finally we'll have this to be the schematic. So now it should be clear, right? This buffer is going to allow only feedback and nothing will flow in the forward direction. That's all.
Can't you put a diode, simple diode?
If you put a diode, again, see, your DC biases will also be screwed, and you need to make sure that this diode is forward biased, right? Your signals can go negative also, and here this voltage has to be set properly. You can do it, but you need to set this voltage properly. Okay. So now we can make the two-stage OTA with this. Let me quickly draw that. So the second stage, I am going to put a buffer in the feedback. That's it. No other change. So now let's quickly see how many poles and zeros we'll have. So again, I can set the capacitor voltage C1 independently, C2 can be set independently. But if I set this voltage, the output of the buffer is also set, and this voltage is also set. So the third capacitor voltage cannot be set. So you have only two poles, and that's expected. So the two poles will be at the same location as before, approximately. And now we expect that we don't have a zero, okay? And we can also quickly verify by shorting the caps. If I short capacitor C1, this voltage is 0, so this will also go to 0. Fine. If I short the C2, it's trivial, output is 0. So let's see what will happen if I short CC. So if this is V naught, maybe I'll use a different color. If this is V naught, what can you say about this voltage? That is also V naught, the buffer will force. What is the current in this direction?
minus GM to V naught.
V naught. So this current minus 2 GM V naught is flowing into the output load here to generate V naught. Oops, sorry. So minus GM2 V naught is flowing into the total output resistance to generate V naught. So what can you say about V naught? I mean, V naught will be 0. Okay. So even if I short the third capacitor, the output goes to 0. So which means we don't have any 0. And that's all. That's something we should expect intuitively. So we don't have any 0. Okay. So this is all nice and good, but finally we'll have to implement the buffer using transistors. So let's see how we might start that. And what is the simplest buffer you guys know? Common drain, right? The source follower. So I'll make that. So this is our GM2. Space here. Capacitor here, and then here I should have the buffer. Some space. Okay. See, this is some. See. So this is our voltage buffer now. So of course this is not a ideal buffer. So how does it different from an ideal buffer? What are the non-idealities?
Gain is not 1.
Yeah, first of all, gain need not be 1. But the gain can be made equal to 1 if you kind of make all, R0 of this guy infinity and stuff. Right? I mean, remember, if you have a common drain configuration, let's say you have an ideal current source also. What is the actual small signal gain of this? No. If I mean, remember, if I were to draw the small signal equivalent, I'll have this is V in, this is V out. So this will be GM times V in minus V out. So drain is short. And along with it, we also have the R0 of the transistor from source to drain. Drain is ground. Okay. So if I were to have V in to be equal to V out, the current flowing should be 0. And when will the current go to 0? If R0 tends to infinity. If R0 is very, very large, the gain is roughly 1. So I can say can be made close to 1. Okay, not a big issue. What is the second non-ideality? Output resistance, right? What is the output resistance of this guy? No. Output resistance looking here. What is it? It's 1 by GM of the transistor MC. For an ideal buffer, this must have been 0. So basically, if I were to model this, our source follower, it is like a buffer with a finite output resistance. Okay, so I'll call it some RC. So this is this, right? So now we no longer have this as the schematic. Along with the buffer, I have small resistance. So let's see what will happen because of that. This is my second stage. I'll also draw the first stage quickly. This RCCC. Okay. Now again, we can try to find how many poles and zeros we have. I can set C1 voltage fine. I can also set the voltage across C2. and I can also set the voltage across CC. There is no contradiction, right? Because this buffer is only going to set this voltage. This voltage is free for you to set. So how many poles we have? We have 3 poles because I can set the voltages across all 3 capacitors independently without any contradiction. So we have 3 poles, and it turns out if you actually work out, the first 2 poles will be same as before approximately. So we now have a third pole due to the addition of RC, that is this extra resistance, and as we will see in some time, this usually comes at a higher frequency. Okay. So this is about the poles. What about the 0? Do we have a 0? So again, let's quickly check it. If I short C1, output is 0, no problem. If I short C2, output is again 0. So let's see what will happen if I short CC. See, in earlier case, when I shorted CC, this output was also set to V0, and that's what gave us this equation and made output 0. Okay. But here if I short CC, this is not set to V0, right? If this is V0, this is no longer equal to V0.
When there used to be no buffer and nothing like that.
Right.
That time also, if we short CC, it should be output should be 0.
Yeah. That time we will have.
Then why?
No. But that time the output is not 0 because this is like a 1 by GM resistance. You think about it, right? Please think about it. We'll discuss later. The fact that we have put the buffer is what prevents the 0, right? Please think about it. But anyways, coming back to this, so if I short this guy, the output will not be 0 now. Is that okay? You can also work it out, but so we'll definitely have a 0 now. But I mean, having a 0 is not a problem. What kind of 0 is a problem? RHP 0. So let's find out where the 0 is, right? That's what we should do. So again, to find the 0 location, I will do the same thing. I'll assume the output to be 0. So if I call this voltage to be some V1, I'll call this to be some Vx. So if this voltage is V1, what is the current here?
Minus V1.
GM to V1. Okay, so this minus GM to V1 is flowing to the output resistance here, which is G2 plus SC2, to generate V0, which is 0. So V1 must be equal to 0. So this guy is 0. Okay. So now if I apply KCL at this node, what do I get? I have Vx times SCC plus Vx times 0. So again I have two conditions, 1 plus SRCCC B0. I mean, I can have Vx to be 0 or the second term to be 0, but if you think about it, if Vx is also 0, the current here is, if this is some V in, this is GM V in, right? So currents in these branches are 0. So this current has to flow here and generate a voltage Vx. Okay? Because Vx is some GM V in by SCC. It's a minus sign probably. If I say Vx is 0, I am saying V in is also 0. That's not possible because V in is not 0. So only possibility is second term is 0. So what is the 0? Okay. So is that logic okay? So I mean, till this point I guess it's fine. right? So now this can imply either Vx is 0 or the second term is 0. I am arguing that Vx cannot be 0 because if we apply some input, we'll have a current GM Vin coming out of the first transconductor, and this current has to flow into Cc and generate a voltage Vx. So Vx must be this, right? Current here is GM Vin. So Vx is minus GM Vin by SCC. So if I say Vx is 0, I am implying that Vin is 0, which is not possible. So the 0 is now in left half plane or right half plane?
LHP.
So we do have an LHP 0, which is actually good. Okay. So in fact, if you write the transfer function, you might have something like this. So A0 by 1 plus S by Z1 times I'll have 3 poles. Okay. And remember, RC was basically the output resistance of the buffer. This was some 1 by GMC, 1 by GM of the source follower, right? RC is the output resistance of this guy, which was 1 by GM. So the 0 is now located at some minus GM by CC. So 0 is now under your control. Okay. So where can you place this 0 now? I mean, it will appear at LHP, but if your GM is now under your control, so this is your transfer function you have. So where would you try to position the 0 to get a better performance? We can basically use it to cancel P2 or P3, isn't it? So you can try to keep it close enough to P2 or P3 so that the effect of one of the non-dominant poles will get cancelled. Okay. So where can I write? LHP 0. Can be used to cancel P2 or P3, whichever is convenient. Now this is all nice and good, but there is one practical issue in using this source follower because of the following. See, if you just have the second stage, which is a common source stage, what is the minimum output voltage we can have here? Overdrive of that NMOS, okay, at some particular current. So now what we are doing is we are taking the second stage and we are adding a source follower, and this goes something like this, right? This is our output and we are adding that source follower here. So let's say this is some MC and MD. So now what is the minimum output I can have? VGS of C plus overdrive of MD. So along with one overdrive, we also need to spend one gate to source voltage. That will severely limit your swing limits, especially in lower supplies. Okay. So this is one reason we almost never use source follower at the output stage, right? Because we have a VCVS with us. You could easily put a voltage follower or a source follower and try to make a VCVS, right? But in practice, we almost never do it because of this swing limit reason. Okay. So because of this technique as such, although works, is not very popular. Okay. So I'll quickly show the common technique that is used. Where is copy here? See, the problem now is this guy. So the thing is, okay, let's see, we'll remove this buffer and see what happens. Seems logical. So now again, you can find out, you'll have again 3 poles. The first 2 poles will be at the same location as before. We'll also have a third pole due to RC. Now let's try to find out where the 0 will be at. So let me erase all the clutter. So again, for finding the 0, I'll assume the output is at 0. So if again this voltage is V1, what is the current flowing here? Minus GM2 V1. What is the current flowing in this direction? Yeah, okay, let me write it then. So we'll have minus GM2 V1 coming from the transconductor, plus I'll have V1 by RC 1 by CC. These two will add to 0. I mean, now we have the feed forward path because we don't have the buffer. But let's see what will happen to the 0 now. So let's quickly work out. So what I'll have, minus GM2 V1 plus SCC V1 by to be 0. So this is minus GM2 plus minus S GM2 RCCC plus SCC 0. Okay. So the 0 will now be at what? 1 by, sorry, GM2 by, yeah, what is it? GM2 by 1 minus GM2 RC CC. Okay. So I can simplify it like this: 1 by GM2 minus RC times CC. Just a simple algebra, you can work it out. But here you see that if I choose my RC to be 1 by GM2, what will happen to the 0? It will basically disappear. Okay, so we'll no longer have that RHP 0. So this is one way in which you can actually eliminate the RHP 0. But is there something better you can do? I mean, if I choose RC to be exactly 1 by GM2, the 0 vanishes. But is there a better choice for RC? Can I do something better? I mean, RHP 0 is a problematic thing. What kind of 0 is good thing for you? LHP 0 is good. So can I choose RC to be if I choose RC to be greater than 1 by GM2, the pole basically comes to LHP. So then you will have an LHP 0. So again, like we saw in the last case, you can position this LHP 0 so that it cancels one of your non-dominant poles. Okay. So this is the common technique that is used. So just put a resistor in series with the capacitor and you choose it appropriately so that either you eliminate your RHP 0 or choose a large enough value so that you introduce a left half plane pole. Cool. So one last thing before we leave. So of course, as I mentioned about the poles, the first two poles will be approximately at the same location, right? But can you tell me what might be the third pole be? The third pole is basically due to the addition of RC. So it makes sense, it should have some RC term, right? I mean, see, at this point things become complicated. Should use some simple, intuition and qualitative analysis, that's all. So third pole is coming due to RC. So I expect some RC term in the denominator. So what is the total capacitor RC sees? So across RC, what is the total cap connected? So these two guys in series with C2. I mean, I have R, I have basically this, right? So across R, I have all these capacitors in series. So roughly you will find this pole will be at this location. Again, it's a very approximate expression. And if you have to actually find the transfer function, we can actually go and do, but see, you have already found the transfer function without RC. Now we have introduced RC. So is there some clever way in which you can compute what the transfer function with RC will be? I mean, you can again sit and write KCL and find it, but I'm asking, you have already found the transfer function without RC. Now in series to CC, I have added a new resistor RC. Is there something you can do to find out this transfer function quickly? So what he's saying is, see, earlier we had the impedance CC. So this provided 1 by SCC. So in place of it, we now have this. The impedance is RC plus 1 by SCC. Right? So this is basically 1 plus S. So now what can you do? I mean, before I had 1 by SCC, that has now become this. So with this I found some transfer function H of S. To find the new transfer function H hat of S, what can I do? I can basically replace SCC by the new term. Okay, that's all. You don't, I mean, you can sit and compute, but that's waste of time, right? So wherever you find SCC, you replace that by this term. That will give the new transfer function. Okay, cool. We'll stop here.